Hello, and welcome to Data Understanding and Visualization in Python for Beginners. You might have noticed that today more and more organizations are opening up their doors to data science and unlocking its power. And that in turn is increasing the value of data scientist who knows how to tease actionable insights out of gigabytes of data. It is becoming clear day by day that there is enormous value in data processing and analysis. And that is where a data scientist steps into the spotlight. The end result of all that data science pipeline is basically predictions about some upcoming event normally. But in this particular pipeline, there are a lot of milestones that one have to achieve. And one of the most important milestone is data understanding that actually consists of data preparation, data cleaning, data pre-processing, and a basic and first level understanding of the behavior and the patterns inside the data. And most of the time, whenever possible, data understanding actually is achieved by data visualization in most of the cases. So and data understanding before actually applying any data science models, machine learning models, is one of the key ingredients and one of the key step uppers in the accuracy of all that kind of models. So in this particular video, we are going to talk about Pandas library in Python. That is actually very, very handy and very powerful library, very powerful package to actually manipulate and understand and clean and pre-process all the data. In our next video in the same series, we will talk about visualizations and the packages related to that. So let's start by data understanding using Pandas. Basically, this Pandas package built on top of NumPy. And NumPy is really powerful package for actually working with arrays in Python. There are other arrays or list packages, list variables and sports is there in Python, but NumPy is really faster, really faster. So basically, the one reason of this NumPy to be faster is it actually each NumPy array basically consists of the same type of data, and that way you need not to record for each data object, you need not to record its metadata individually, but the metadata is actually recorded for whole for the object just at once. Further, there are universal functions inside NumPy that are really fast, a vectorized code that work on the same type of object really quickly. And it is good to just go through and get comfortable with NumPy first before moving towards Pandas, because a lot of indexing, a lot of kind of methods that we will see in NumPy, they will straight carry on in Pandas as well. So let's start by NumPy. So you can import the NumPy package, and one of the standard renamings or aliases is np. You can have your own alias as well, but np is somewhat more standard. You can create a NumPy array by np.array function. You can provide a list inside, and you can just generate array through a list, or you can generate an array through a tuple. So let's go to basically the Jupyter notebook and actually code it and see what happens. So let's first import NumPy as np, and let's print the variant of it. What variant basically we are using? Let's see that. Right now, at my system, the NumPy variant I'm using is 1.18.1. Let's import Pandas as well, although I haven't introduced that yet, but let's just import that. as PD, and let's check the version of Pandas as well. So that is 1.0.3, the version that I am using here at my system. So let's first generate an array. Let's just first generate an array. A equals, let's say, np.array, and let's generate the array using maybe -8 and stuff like so. Yeah. So that's the array. So if you just see different kind of attributes in the array, so a dot, for example, d type, what's the data type of this array? So you can see it's integer 32. It's a 32-bit integer, although you can set the data types here. You can generate the array using a tuple as well. So you can, a tuple is defined in parentheses, for example, 2, 3, 5, 6, 7, and 8, let's say. So you can generate that. So yeah, so that's the NumPy array. At a very simple and basic level, that's what the array looks like. I should also mention that you can generate, for example, you can work with lists. For example, you can generate a list, 3, 4, 5, that's a list. That's perfectly okay if you just see the type of L, that is list. And if you see the type of A that we just generated above, that's the n-dimensional array of NumPy. You can work whatever work that you are doing with NumPy arrays, you can do that the same thing using lists. But lists basically can store heterogeneous type of data. You can have, for example, a string variable here, ABC, or another variable of another object of different type here, for example, any object. I mean, you can have heterogeneous type of data inside the list, and that basically brings a necessity to record the type information and the storage information of each object in the list separately. And it might be difficult to apply a generic function for doing a particular stuff for all these different kind of objects at once. NumPy array, on the other hand, has all the objects of the same type, which means you record all the type information just once for the array rather than each object individually, rather than each element individually. And then you can have specialized vectorized kind of codes that are really faster for a given particular kind of data type. So that's how you define your NumPy array. You can just print the values, print A, and it will, for example, give you these kind of values. Yeah. So next, what we see is basically, let's see how can you see different kind of properties, like what is this property ndim inside this? Can you define the arrays that are multidimensional? Can you define arrays of arrays and arrays of arrays of arrays, or something like so? Because as I mentioned earlier, as long as you have same kind of objects, you can place those objects and define a NumPy array. What if my objects themselves are arrays? So that's my one object or element. That's my one object or element. That itself is an array. If I place these objects, because they have same type, all of them have same type, they are array objects. And if I build an array on top of that, that basically is called array of arrays, or sometimes called two-dimensional array. Now think about if I have two-dimensional arrays, several of them. Now again, a two-dimensional array is an object. If I have similar kind of two-dimensional arrays, several of them, maybe 2 of them, 3 of them, and I have an array of those, that is also possible in NumPy because each object has the same type. And then we will say, okay, that's a three-dimensional array. So let's play with that in Jupyter Notebook, just to get comfortable with the dimensionality of the array. So let me define, for example, let me define an array A. Let me define that array as, let's say, 1, 2, 3, and 4. That is, right now it's a list of 4 numbers, or assume just it's an array with 4 elements. Define another array, for example, 3, 5, -7, and let's say 0. That's an array of, these are basically, that's one array, that's another array. If I just wrap them up in one bigger array, then the first array basically is an element now, the second array is an element, and now this outer array basically contains 2 elements of same type, and you can now define the np.array on that. You can just create an array on that, and in this particular case, that's a multi-dimensional array. If you print dim, you will get 2, because the dimension of this array is 2. Dimension basically is how many levels you are going in. So for example, here we have 2 levels of arrays inside the arrays. If we have arrays inside the arrays, and we have these are elements in a larger structure of arrays, then the dimension just goes high. So let me take that example as well. So let's say we have A again. Let's say we have an array 1, 2, 3, 4. Let's say that's an array. Let's say we have another array. Let's say 3, 4, 5, and 8. Maybe we can have another array. Maybe 1, 2, 3, 4. Oh, that I already have. So let's just change the numbers. 8, 7, and 2. Let's say these are one-dimensional arrays. Now think about that. That's a 2-dimensional array. Yeah, array of arrays. Each array now is an element in a bigger structure. Yeah. So now think about the same kind of structure if repeated. It's the same kind of structure. Just we pick that, Control C and Control V. We might be having different elements here. Maybe we have all the elements. Maybe just go negative, just to think about that these are different elements. Yeah, minus and maybe -7. Yeah. Now you can see this is one element. This one element is basically a 2-dimensional array. That's another element. The 2 elements have the same type. They are exactly of the same type. If I wrap them up in a bigger structure on an array, we will say that's a 3-dimensional array now. And now we can just build an array on top of that using NumPy.array. By the way, if we do not call the NumPy.array function on top of that, that's a multi-dimensional array in form of list. So that's an array A. If we now see the dimensions of A and dim, that is 3. Apart from the dimensions, there's another property called the shape property. Shape basically tells you how many nested structures you're going in and how many elements are there. So let me give you an example here, just right now what we have done. What we have is we have 2 elements of 2 dimensions. Basically that's a 2-dimensional element. We have 2 elements that are 2-dimensional, so 2 of them. Now in each 2-dimensional element or 2-dimensional array, we have 3 1-dimensional arrays. Okay, so we have 3 1-dimensional arrays in a 2-dimensional array, and in each 1-dimensional array we have 4 elements. So if you now print the shape of A, it will print as the following. How many higher level structures are there? Well, there are 2. In each higher level structure, how many 1 low level structures are there? Well, in this case there are 3. Then in each one low level structure, how many elements are there? Well, in this particular case there are 4. So the shape will be 2, 3, 4. So let's see. Yeah, so 2, 3, 4, and you can simply relate that as there are two two-dimensional arrays, and in each two-dimensional array there are three one-dimensional arrays, and in each one-dimensional array there are 4 elements. So that's what the shape of A is. Now if you for example call this shape and just pick for example 0, it will print the high-level structures, A dot shape 1, the structures inside the high-level structures, these are 3, and A dot shape let's say 2, these are the number of elements in each one-dimensional array. Yeah, so so that's what this shape is. Next is how can you access different elements in this array, NumPy array. Let me go back to Jupyter and just to give you a look and feel of what this basically looks like. So if we move back here, let's say we really type the following, and then we say what that means. Let's say 0, maybe 1, 2. Let's say what that means. That means this first index shows that pick the 0th element in the highest structure. So remember in the top structure we have 2 elements, 2 one-dimensional arrays. That's the element indexed with 0. That's the element that is indexed by 1. So when we type 0 here, we are picking the first two-dimensional array. Great. So now we are here, exactly here. Now let's see what's the next index is. The next index is 1. Now we are inside the first structure here. Now the index is 1. So this one-dimensional array has index 0. This one-dimensional array has index 1. This one-dimensional array has index 2. Because we have typed 1, so that means we are targeting this one. Okay, now we have targeted this one. Now which element? Element that is indexed by 2. Because the indexing starts from 0, so the element that indexed by 2 is basically the third element, and that is 5. So 5 will be accessed with this command. Yeah, so that is 5. See that? So that's how you can access individual elements in NumPy array, or not just NumPy array. The indexing is more or less, in this particular case, is more or less same with other kind of array structures as well. But I just want to show you all this stuff in the context of this NumPy. Next, there are certain functions that are great to have. There are certain functions that can generate this arrays for testing very quickly, and can do certain permutations on those, and reshape a single dimensional arrays to multi-dimensional arrays and vice versa. So it is good to know some of the functions that are available in NumPy just for array creations and manipulations. So one function is basically arrange function. So np.arrange. np.arrange, if you just supply, for example, 10, that means generate an array of NumPy array with values start from 0 to 9. 10 is not included. So they are integer values, start from 0 till 9. So if you print A, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Further, if you, for example, call the same function as np.arrange, start from 2, end at, let's say, 100, and take the jump of 10. Well, that will generate the following. It will start from the number 2. It will keep on jumping with 10 elements until it reach 100, and the 100 is not included. So the first element here will be 2. The second element after the jump of 10 will be 12. then you take a jump of 10, then you are at 22, then you take a jump of 10, then you're at 32, and so on, and then you're at 92. So this arrange function basically has this first value as starting index, the starting number, that's or sometimes called the lower limit, the second value as the upper limit, and this is the step size. Remember always that the upper limit is not included. You have to stop right before the upper limit. So upper limit is not the part of the array always. So this is the arrange function. There is a random package in NumPy, np.random. So that's a package. And there are some fruitful functions in those as well. So one function is permutation. It is sometimes necessary that we want to generate certain arrays that do not have a particular order just to check performance of our algorithms. So for example, in here what will happen is this np.arrange function will generate an array in a particular order, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And this permutation function actually just randomly permutes it, and the whole array will just shuffle up, and you will get this. So this permutation function is helpful for permuting any NumPy array in random order, in basically randomly. This permutation happens actually randomly. There is another important function, although there are several, but just I want to focus on reshape. So for example, np.arrange, let's say that is let's say 100 elements, and you just reshape that to, you just want to build a two-dimensional array to work on that. And these are 100 elements. What you do is you reshape that into 25 by 4 array. So that basically becomes a two-dimensional array just for testing purposes. So this reshape function actually reshapes all this array structure into a two-dimensional array, or maybe in a three-dimensional array, whatever you want to do. So this reshape function actually picks those values in the array and just arrange those values in this particular format, whatever that format you supply. Now, one thing you must remember that the total number of elements in the array must match the total number of elements in the reshaped array or reshaped matrix, whatever that is. Here we have 100 elements in total, starting from 0 to 99. And when we want to reshape, we want to build an array of 25 rows and 4 columns. So the total number of elements are again 100. If accidentally we mismatch this, we'll get an error. So for example, np.arrange 100.reshape, for example, if I say, okay, reshape it to 25 by 5. So that cannot happen because 25 by 5 actually is expecting 125 elements, and we have just 100 of those. So how can 100 elements can be arranged in any way to generate 125 elements? It's not possible. So yeah, so these are some useful functions. I thought I should tell you some of these just to get comfortable with NumPy. Next, we talk about the indexing, or sometimes called the slicing in NumPy. What if you want to access multiple elements at once from the array? There is a very cool way in Python to access the arrays. If you have an array variable, let's say a, and you give a start index, then colon, you give an end index, colon, then you give a step size, just as we have seen in arrange function. Then what it does basically is it picks all the elements starting from the start index, ending at just one index before the end index. But remember, end index is never included. End -1 is included. So start from the start index, go till end, do not include end. And if you have some step size provided, then pick those steps, pick those jumps. If the step size is no longer there, then basically the default step size is 1. If start index is not given, then the default start index is chosen to be 0, the very beginning. If end value is not given, then the default value for end is chosen to be the very last index of the array. So there are default values as well. So start, the default value of start is 0, the default value of end is the last value, and the default step size is 1. So let's see some examples just to get comfortable with this indexing, because this indexing stays as it is in Pandas as well. And people say, some of the practitioners, they say those who actually have good grip on NumPy slicing, they actually work, they actually will be having eventually very good grip on data science packages as well. Well, some of the people just think like so. So it is good to spend some time to understand the indexing here. So so take for example here, let's say A is some array, NumPy array, and I just index it with the start as this 1, start index is 1, and the end index is 5, and the step size is not provided, so the default step size is 1. Here 1 does not mean the first value, because the indices, they start from 0, so it will pick all the arrays starting from index 1, which means the second element, till the index 5. But the index 5 is not included because as a convention the end value is not included. Now on the other hand, if you have for example A where the start is missing, that is by default considered as 0, and if the step is missing, that is by default considered as 1, and you have to go to 5. So go from the very start index, which is 0, and go till 5, do not include 5, and take a jump of 1. So this is the same as if we write a 0 there. So if we write a 0 there, that's the same thing. So now if you have 2 colon something, 2 means the starting index, so start from index 2, colon nothing means go till the end, include the last element as well, and take the jump of 1. This is one very fancy way of just reversing the elements. If you give a negative step, the role of start and end in NumPy, it just reverses. So if you give a negative step size, then the start becomes an end and end becomes a start. So in this particular case, for example, start from the end, start from the last element, reach to the beginning and take the jump of -1. So it will actually reverse the whole array. In this case, you take a jump of 2, and this particular is an example of two-dimensional array. If A is two-dimensional array, then there are 2 indices, the first dimension index and the second dimension index. So let's go to our friend Jupyter Notebook just to play with and get comfortable with all these kind of indices that we have just seen. So let's say A is some array, np.random maybe np.arrange, np.arrange. Let's say it's an array of 10, size 10, and let's say we have some of its random permutation, random.permutation. So yeah, so let's say A is that, just print A here just to see how the elements they look like. Now if I just access, for example, 1 to 5, just like so. So what it will do is it will start from 0, because 0 is at index 1, then 4, then 1, then 3, I guess, because 1, 2, 3, and 4, and 7 will not be printed because the last index is not included. So that's what it is. However, if for example I just apply start from 1, go till, let's say, 7 and take a jump of 2. Now it will start from index 1 and it will print every other element. It will access every other element until it reaches the index 7, where 7 is not included. So index 7 is not included. So that's how it goes, by picking every other element. So it starts from 0, then it picks 1, then it picks 7, and then it stops basically. Similarly, if we have, for example, a, and we say okay, -1, well, it will reverse the array. If you see the original array, that is 9, 0, 4, and 2 was at the end. If you now see this 2 is at the beginning, and all that stuff. And yeah, so what if we have two-dimensional array? Let's take an example of two-dimensional array. A is np.arrange, let's say 20 elements, and dot reshape, let's say 20 elements, let's reshape them by 5 into 4. So that's, let's say, A. So now if we, for example, say okay, A 2, 3, that means the second row, in this case, not the second row, the row at index 2, which is the third row. And in this third row, pick the element at index 3. So the element at index 3 is 11, because the indexing start from 0. So yeah, so that's 11. Next, what we can do is, for example, let's say we have A, and what we do is we, let's say, pick all the rows starting from 1 to 3, all the rows starting from index 1 to 3, which means this is index 1, this is index 2, this is index 3. So let's pick all the rows, all these 3 rows, and of these 3 rows, let's pick just the element that is index 2. So just pick, for example, this element 6, 10, and 14. So let's see how it works. Yeah, so it is 6, 10, and 3 was not included because we start from 1, we go till 3, the last index was not included, so only the 2 rows, this row and that row, they were selected. And with these rows, just I pick the column with index 2. What if I just pick these 2 rows, and then what I do is I say okay, 1 till 3. So what it will do is it will first pick the row with index 1, then the row with index 2, these 2 rows. So let me highlight both of the rows, these 2 rows, and then it will in these 2 rows it will then pick the columns starting from index 1 and ending at index 3 but not including 3. So it will pick 5, 6, 9, 10 submatrix in this particular case. So 5, 6, 9, 10, yeah. So you can do this kind of slicing. This is called slicing and indexing and all that stuff. One common way here is to write, for example, if we want, let's say, all the 2 rows and all the columns. So this colon operator is handy to just say I'm interested in all the values in the second dimension. So in this particular case, it basically prints the 2 rows that are selected completely. Yeah, so this column is there. So let's see what happens. Let's see what happens here. What do you think? What will happen? So it will do what? What do you think? Well, it will start from 0, the very first row. It will take a step of 2. It will alternate. It will pick every other row till the last row, and it will access the whole row because not a particular column index is given here. So it will actually access the alternate rows starting from the very first row indexed at 0. Yeah, so that's what it does. So yeah, I mean that's about indexing or slicing in NumPy. We can have more examples, but I guess the purpose just is served. So next, what we do is we talk about some indexing in NumPy that is more kind of sometimes called the fancy indexing or masking or something like so. In fact, in array you can give an index array as well. Rather than giving indices, you can give an array of indices, and the elements that belongs to the elements that are consistent with those indices, they will just be returned. Not only the index array, you can give an Boolean array. I mean the whole array. For example, let's say A has 8 elements, and you give a whole Boolean array, sometimes called the mask. You give that, and the elements that correspond to true values, they will be accessed, and the elements that belongs to false values, they will not be accessed. Further, because the Boolean arrays can be supplied, you can apply a lot of Boolean operations and access elements in that way. For example, let's say A is an array, and you want to access all the elements that are smaller than 8. So what you do is you first do this. You first apply this operation. A is smaller than 8. It will create a Boolean array, and a true will be there for every element that is smaller than 8. And then this A will contain eventually a true, false kind of index array or a mask, and it will actually pick all the elements that are smaller than this. You can combine different logical operators. For example, you can do this. A is less than 8 and A is greater than 4. You AND them, so this is a Boolean mask, that's a Boolean mask. So all the elements that are smaller than 8 and bigger than 4, just select those. Remember, to work with arrays, you cannot use the AND operator as AND. You have to use this AND operator this way. This AND operator is used when the both operands are basically objects and not the arrays. So let's see that. And I also want to discuss one more thing here, that when you do this fancy kind of indexing where you supply the index array inside or the Boolean mask, you actually get a copy of the array. So the new array that you come up with, let's say B, is a whole new copy in the memory. However, as you have seen in the previous way, here if you do the slicing by applying these kind of indices, you do not get a new copy in the array, but get basically a view. So in the memory you have the same array, you just got a different name that points out the same array. Now if through B you change certain elements, because the elements are actually changed in the same array, now you will see the changes will be reflected in A as well. But if you do this masking or array or index arrays or Boolean arrays inside, you by default get a copy. So let's practice this concept in NumPy, just to in Python, just to get comfortable with whatever we have said so far. So let's say A is np.random.permutation and let's say we have np.arrange, let's say 10. So that's our A. Let's say this is A. And now what we do is we access array, but we access only element index with 1, element index with 5, and element with index, let's say 2. So element that is at index 1 is 0. Element that is at index 5 is, I guess, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5. So element at index 5 is 4, and element at index 2 is 2. So that is what is the result. Further, if we want to basically, if you see, for example, A is less than, let's say 5. So the result will be a false, true kind of array. If we do this, let's say we generate an index array, that is a is less than 5. Let's say this is our index, and then we just access all the values in this particular index, so we'll get all the values that are smaller than 5. Not just that, we can generate the index array inside like so, and we are just perfect. We can combine different operations using Boolean operators. For example, a is less than 5, this, and a is less than 5, and a is greater than 2. Just select those elements that are bigger than 2 and less than 5. Just select those one. So you will get those elements inside if they are. So now I'm going to explain the difference between copy and view. So consider, for example, you have a, let's see the a again. You have a, and you just create an array b by slicing. So a, let's say 1, 2, 5. So now b will be having these kind of elements now. Yeah. So basically the first 4 elements of a. Sorry. The 4 elements of a starting from index 1, not the first element, because index start from 1. Now if I change any element in b here, let's say element 2, which is 1. Let's say if I change that element 2 and I set this as -100, then it's perfect to see that b has this change that is there. But what actually happens also is the a also changes. So you can see this a also changes, and that is what we call as a view. In fact, inside the memory, a is pointing to the same data that b is pointing to. B is just another name of the same memory location. Now, if you change any memory location using b or using a, you will see the changes in both the arrays. So care must be taken in these kind of situations, because you might be thinking that all the changes, they are just happening in b, but in NumPy particularly, the slicing actually creates a view rather than a copy. If you want to force to get a copy, you should call a copy function. For example, this dot copy. Now you're forcing that b must be another copy, and now if you change any elements in b, b has now no sharing in memory with a whatsoever. But if you do not call a copy function and you think that it's a separate copy, that might be a disaster in your program. On the other hand, if you, for example, do masking like if you access, for example, b as a into a is less than 5, let's say, so that is b. So now in this particular, if you apply this masking or Boolean array or array as an index, by default the array you get is a copy. By default it's a copy, it's no longer a view. Now if you change elements in b, let's change this element at 0, which in fact is 0. Let's change that to 9. Let's change that value to 999. Now in b you will be seeing that change, but this change will no longer be in a because that is a copy. So if you do this masking or fancy indexing or use an index array, you will get a copy by default. But if you do the slicing, you get a view by default. So this is specific to NumPy, because if you use lists, for example, and you do slicing, you get a copy. This is the NumPy that to improve a lot of operations and to actually build a lot of efficiencies in a lot of operations, it actually work on not creating a lot of copies when you do slicing. But it should be known that the behavior of NumPy in slicing is different than the behavior of the list in Python in general. Next, we talk about broadcasting. Broadcasting is another powerful concept. Basically is to, if you have 2 variables, if let's say a is an array and 5 is just one number, Now, if you want to add a number to array, what should happen is the number should be copied in another array, and the two arrays should be of the same size, and then the addition can happen. So for example, if A is 1, 2, 3, and if you want to add a 5 to it, then what you should do is like this. So you have to make an array of all the 5s to make the sizes same, and then you have to add it. Broadcasting is the same concept, but it does automatically. It broadcasts basically this 5 to become consistent with the size of A and get what you want to do it. So it happens implicitly inside. But care must be taken. In certain situations, the broadcasting cannot happen. For example, the broadcasting can happen if you have, let's say, 1, 2, 3, 4, a matrix, a two-dimensional matrix, two-dimensional array, and then you have a value, let's say 2 and 7. In this particular case, this 2, 7 will be repeated, and the 2, 7 will be added to the first column, and the 2, 7 will be added to the second column, and this column will broadcast, or basically you get a copy of it, and everything will happen. In this case, it can happen. But consider, for example, this situation, 1, 2, 3, 4, and you want to add inside this as, let's say, you really want to add, for example, 1, 2, and let's say maybe 3. Let's say this. This is not possible. I mean, these are not the. I mean, this is not going to extend. This is not going to extend to, for example, if you want to extend this, you will extend this like 1, 2, 3, 4, and then it is inconsistent. And yeah, I mean there are issues in certain cases. Broadcasting cannot happen, in which, remember, when broadcasting happens, it happens on the whole object. The whole object get repeated, the whole object get broadcasted. If the broadcasting of a particular object make another object that is not consistent in size in no matter what way, in that case the broadcasting cannot happen. But in most of the cases, it is really natural to just broadcast and forget about what things are happening inside. For example, let's say in np.arrange, let's say 20.reshape, let's say 5 by 4. Let's say this is my matrix A. So that's A, and I just say, okay, A plus 5. So that means add 5 to all the values. Not only that, if I just want to have, for example, let's say, so this A dot shape basically is 5 by 4. So basically it has, each column has 5 elements. We have 4 columns. Each column has 5 elements. If we, for example, make an array B, let's say np.arrange, let's say 5 values dot reshape into 5 by 1. So if you see b dot shape now, you will get a 5 by 1 matrix. If you now add A and B, this column B will be repeated or broadcasted, and the sum will eventually happen. So this is really powerful. I mean, you need not to actually repeat this B to make another array and do all that stuff. This broadcasting actually take care of all these kind of things. And later in Pandas, we will see that this broadcasting is really powerful there as well. Let's see some more useful function in NumPy before actually moving towards Pandas. For example, this hstack function, if you have 2 arrays and you want to concatenate them together using, if you want to concatenate them together horizontally, you can use this hstack function. You can use this vstack if you want to concatenate them vertically, if you want to stack one on the other. You can use vstack, you can use sort function, there are arg sort function, there are a lot of universal functions that are there in NumPy. You can do that. You can have a concatenate function with access that can actually simulate this H stack and V stack together. So and there are a lot of other functions. We can spend the whole course on that, but I'm just switching towards Pandas now. So let's go towards Pandas. I mean, Pandas basically is a very high-level package that builds on top of NumPy. So all the things that you have seen in NumPy, they are actually carried out in Pandas as it is. But the power of Pandas basically is it can handle string kind of data, it can handle numeric kind of data, very heterogeneous kind of data sets. Yet, I mean, even though it can have a lot of heterogeneous kind of data sets, it can work with large data files, even though the speed and the efficiency of Pandas is just like NumPy, it is no way closer to lists or something that can handle heterogeneous kind of data. So Pandas has, basically Pandas has three kind of objects: a series objects, a data frame object, and index object. But in this particular tutorial, we will be focusing primarily on series and data frame. So a series object, if you just, by the way, we have already imported Pandas. If you want to import Pandas again, just to check, for example, import Pandas as PD. So that's how you import. You can rename this PD to something else, but PD is something like standard. Most of the people are using that. If you want to check the version of Pandas, at my machine it is 1.0.3. So that's what the version of this is. So now if you call this series function, it may look like to you like the np.array function, where these are the values. But what in series, what you can do is you can give explicit indices to each values. So in NumPy array, for example, you have 0.25, 0.5, 0.75, 1.0. The default index of the first element is 0. The default index of this element is 1, and so on. But now you can index them. You can give explicit indices. You can give meaning to indices, and you can later access those values using these indices. If you're familiar with dictionary in Python, it is much like dictionary. I mean, these indices, they act as keys, and they act as values. But overall, the difference between NumPy array and a series array basically here is you can define explicit indices. Let's see an example in Jupyter. So let's say we have a as pd dot series, and then what we do is we say, okay, what kind of data we have? Let's say 2, 3, 5, and 6. That's our data. What kind of indices we want for this kind of data? Let's say we want indices as A, that's index 1. Let's say B, that's index 2. C, that's index 3. And let's say D, that's our index 4. So that's A. If we just check the type of the A, that's a series object from Pandas. Further, if we just say A dot values, what are the values? It actually gives me all the values. And if you see the type of A dot values, if you see the type of that, for example, that will be a NumPy array. So type of these values, that's a NumPy array. Yeah. And if you see the index, A dot index, that's this. And if you see the type of A dot index, it will be an index type object in the Pandas core, like the series. So that's what it is. So the basic difference here is you can now access different elements using their indices like so. You can access those, you can, I mean, and all the operations that you have seen so far, they're there. I mean, if you want implicit indices, you can just go, okay, I want to access these elements. And now the implicit indices is also, I mean, supported. In this particular case, the index of 2 is 0. So the implicit indices are there. And on top of that, you have indices, string type indices or descriptive indices that you may want to work with. One difference, however, is to be noted that when we use slicing in implicit indices, this final index end is not included. But if we do the slicing, we can do the slicing on explicit indices as well. Let's say we want to go from A to C. That means start from index A, go sequentially to C. In this particular case, the last index is included. That might be a confusion, but you must know it. I mean, if you use implicit indices, the end is not the part of the array, end index. But if you do the slicing using explicit indices, the end index basically is the part of the array. And yeah, I mean, you need to know it. So yeah, so that's just the series object, which is like the one-dimensional array in Pandas. It is like one-dimensional array like NumPy. In this particular slide, I'm going to show you the data frame object. That is basically more tabular, two-dimensional array, can handle text data, can handle individual, I mean, it is all kind of spreadsheet-like view of the data that is available, and you can handle different columns individually, you can handle different rows, and you can just work a lot like you're working with file or spreadsheet, like so. So here I'm going to make a dictionary. For example, this A is a key, 4 is a value, A minus is a key, 3.5 is a value, and all that stuff. That's a dictionary. Let me call that dictionary as grades dictionary, or that's PD. Then I will define a series object on that. Then I can make a marks dictionary, and I will do that. And then eventually I'll be able to make a data frame object, let's say RS, using the two series objects. So let's make two different series objects, and let's then basically make a data frame object. So let's go to Python and do that. So let's say grades, let's say is pd.series. I can make that directly. The grades are, for example, 4, 3.5, 3.5, and maybe 3, and maybe 2.5. These are, let's say, grades, and the indices of these grades are basically, let's say, this is A grade, this is A minus, this is B grade, and let's say this is C grade. Let's say that's a series object. Let me call that as grades. Let's make another series object and call that as marks. Just, let's say, student grades and student marks. We can do the same thing using dictionaries as I've shown you in slides, or we can do that directly here. So let's say this is 85, and maybe then let's say this is maybe 75, and maybe this is 65, and this might be 55 maybe. So these are two series objects, both have same kind of indices, or like, and now I can make a data frame object. Let me in the marks sheet, or the sheet, let's say. Sheet is let's say pd.dataframe, and pd.dataframe, and inside that we actually make a dictionary, and we say, okay, grades, or let me call that column as grades, grades. The value of that is grades, and then I can have another, for example, column, let's say marks, and the value of this is that. So now with that, if you see the sheet here, if you see the sheet here, the sheet looks like really tabular. I mean, this A minus, this A minus, B, and C, they are kind of indices to different rows. And this GR, MR, these are, I mean, different columns, and you have a two-dimensional data frame in this particular case. So this data frame is really powerful. I mean, it can, later we will see that if you have CSV files or the data is there in the files, you can just load those files, and in this Pandas, the files will be loaded in a data frame, and the data frame is just tabular and has a lot of functions to actually manipulate the data and deal with that data. So yeah, so here I just give you, for example, I have this sheet and I want to access its column, let's say GR, and all the column will be available to me. Yeah. So if I want to see what are the columns, what are the column names of my spreadsheet, or here it's data frame, then I can see the columns. I can see the values, sheet dot values, and this will give me all the values inside the matrix. If all the values are numeric, no problem, I can have those. I may have other, for example, values like index. Here I have row indices like A minus, B, and all that stuff. So yeah, so we can also produce new columns if we want. For example, sheet. Let's say I have a new column. Let's say the column name is new column, and there we can have, for example, we can just, for example, have np.random.rand int. Let's say the random values are from let's say 1 to 10 maybe, and how many values are there, how many rows we have added? 4. So 4, and the new value, the new column is just added there. I mean, now you have another column, new column, with these values. I mean, this is that simple. I mean, it's very, very comfortable to work with data frames. You can add new columns, you can see individual entries, you can drop the columns, you can rename the columns. If you just want to rename this particular column, so let's say sheet dot rename, then what do you want to rename? Columns. I want to rename my columns from new C to, let's say, column C. So oh, there is a problem. Yeah, I know the problem. So this should be this. So now that is there. I mean, it is renamed as col C. Yeah, I mean, this is a huge sport in there in working with data frames. I mean, you load the data in a CSV file, and you have just very good grip on each and every element, different substructures, different rows, columns, individual entries, and all that stuff. So it's really powerful, I mean, to work with this kind of stuff. Further, as you have seen earlier, if you remember, we use this Boolean indexing. So what if I use the Boolean indexing here in this sheet? So for example, sheet, give me all the sheet where the sheet marks, where the marks column has smaller value than, let's say, or bigger value, let's say bigger than 70. Give me the subsheet, or give me the sub data frame where this condition is true. And this condition is primarily saying, go to this marks column and see what elements satisfy this condition. For those elements, just pick all the rows and discard the rest. And here, if you see, you'll get the 2 rows back. So it is kind of same kind of Boolean indexing that you were talking about earlier. Yeah. So It's really powerful, really powerful. Next, we basically move to another problem of implicit and explicit indices. It is possible sometimes that maybe due to certain reasons, you define your explicit indices in defining the series in such a way that the explicit indices, they are basically numeric. And for example, the explicit index is 1, the explicit index is 3, the explicit index is 5 for the values A, B, and C. Now, if you access a particular value, if you access a particular value here, like this, if you access this value, it will refer to explicit index. So for example, this 1 is index of A. So it will pick that. Happy scenario, great. But if you slice, if you do the slice notation, by default, the slicing goes to implicit indices. So that means start from the implicit index 1. The implicit index 1 is here. And go till 3 and do not include 3, which means B and C will be printed. So this is a huge problem. Sometimes if your indices are numeric and there is a confusion between explicit and implicit index, and the source of confusion basically is if you do slicing, it always goes to if you do slicing and your explicit and implicit indices, they are numeric, it will by default go to implicit one, and that may brings a source of confusion. To handle that, Pandas actually give you two kind of functions. One function is called LOC, or location, that whenever you call this particular function, then that means you're using explicit index. So for example, data.log, and then you say, okay, 1:3. That means use explicit indices for sure. On the other hand, if you use ilog data.index location, and now you say 1:3, that means use implicit indices. So to differentiate explicit and implicit indices separately, Pandas basically provides two functions, LOC and ILOC, and they are really powerful. I mean, once LOC is called, or ILOC is called, then the rest of the indexing is the same as you have seen in NumPy. So yeah, so let me give you just this particular example let me code this example in Python for you. So let's say we have for example, series object, let's say, and let's generate a series object. Let's say data is pd.series, and let's say the values are A, B, and C, and your index is basically let's say 1, 3, and 5. That's your series object. Now, what do you think? What is this data 1? Data 1 basically will use explicit index and it will return A to you. Great. Wow. So what will be data 1:3? That will use by default the implicit indices, and it will start from index 1, which is B, and will go to index 3, which is not here. The index 3 is not here. So it will stop right before the 3, as the last index is not included. So it will print B and C, which might be unexpected, because you might be thinking that it should print 1 to 3, 1 and 3, which means go to A and go to B. Maybe you're referring to explicit indices, but it is using implicit. So the workaround is really to use log. So data.log. Now if you use 1, 3, you are on your way using the explicit index. And if you use, for example, data.ilog, now you're using implicit indices and all the conventions of implicit indices. So this loc lock function and iloc function, I mean, they're really important to know, because there is a confusion of explicit and implicit index overlap in Pandas. So care must be taken. Next, we talk about these, for example, these missing values. So let's talk about the missing values. It is possible to have missing values inside a data frame. And it is possible that you read a particular file and certain values in a particular column or row, they just are not present. So they are called missing values. How to handle missing values, how to take care of the missing values. Let's see. So let's say we have pd.dataframe, pd.dataframe. Let's say we have one series object or a dictionary, which is the index A has value 1, index B has value 2. And let's say we have another series object, or in this particular case, it is by default a dictionary object, which is 3, and let's say we have C with 4. So that's our object with two NaN values. NaN sometimes is referred to as not a number. There's another data type in Python referred to as none, N-O-N-E, none. That also in Pandas, the NaN and none both refers to as missing entries, and they are also called null entries. Or so let's say if A is that, and you have now A, you have this A, how can you handle these missing entries? There are several ways. I mean, one is you just drop all the entries that contains this, for example, just drop everything, and just drop all the rows that contains the null values. In this particular case, if you see, if you drop all the rows that contains the null values, you actually end up having nothing, and that's bad news. Sometimes it is possible when you have a lot of data and a few missing entries, you may compromise on just dropping the rows that contain the missing entries, and you work with the rest of the data. But in certain cases, you may have to impute the data, or you may have to fill the null values using certain predefined values. For example, if I fill all the values with 0, that means fill all the values that are null, just fill them with 0. So now I'll be having this, and now I can do whatever stuff I really want to do. So these missing entries, they can be there in real situations when you're working with real data. And this Pandas really allows, I mean, I have shown you just a few functions, drop NA and fill NA. There are a lot of other functions that you can basically see to handle or to work with missing values in Pandas. Again, if I just want to know where are the missing entries, I can, let me just generate this object another time. If I have this A and I want to know is null, I just want to know is null. That will give me all the entries that are null. So wherever there is null, it will return me true. Wherever this is not null, it will return me false. Further, I can check the is null on each column individually. So for example, if I go to column B and I say is null, so that will give me the indices on that particular column. So in column B, there is no null entry. However, in column C, if you see in column C, the first entry is null and the second entry is not null. So this may generate a Boolean indexing or Boolean mask for you to further process or fill the entries if you want. If you do not want to use fill NA or other functions that are provided in Pandas. So yeah, so next we talk more about some missing values, and basically we talk about some data frame operations at once. So let me let me just go back to Jupyter to actually talk about one more way of handling these missing values and the operations that can be applied to a whole data frame at once using universal functions. So let me talk about that. Now, so let's say we have some data frame. Let's say df is pd.dataframe, and let's say it's np.random .rand int. Let's say the range of this rand int is 0 to 10, so generate random integers from 0 to 10 and generate 3 by 4 matrix of it, which means generate 12 numbers, reshape them to 3 by 4 and generate that thing. And the columns, just name the columns as A, B, C, and D. Just make these columns. It is good to just apply a list there. Just make a list of these. Just make a list of these value. Just make a list of these elements, and the columns are A, B, C, and D. There are 4 columns. Yeah. So generate that data frame. So let me see that data frame. That data frame looks like this: A, B, C, D, and these are the random entries. Let me generate. Let me apply a particular function, a universal function, from NumPy on all these data frames. For example, let's say NumPy dot, let's say sine function on all the values of the data frame multiplied by np.py/4. So the result will be, this particular operation will be applied on each and every value in the data frame, and the result will be another data frame. You can have another data frame as a result. You may save that result into another data frame. So yeah, so that's the result. So now if you see the type of df2, that's completely a data frame object. Now we have seen already df, and we can apply certain functions on that. Maybe we have multiple data frames and we want to maybe add the values together, and maybe we want to apply addition or subtraction operations on different data frames. How can we do that? So let's say we have a data frame like pd.dataframe, and let's say this is np.random.rand int. Let's say from 0 to 20, and we make a 2 by 2 matrix. So 2 by 2 matrix, and the columns here are is basically list. So just make a list of the columns are A and B. So that's our data frame A. Let's have a data frame B. Let's have a data frame B here. So data frame B, let's say, is again this kind of, let's say 30 random integers, but the size here I'm going to do is 3 by 3. So because there are 3 columns, I'm going to basically add another column, let's say, or maybe renaming the sequence of the columns. So there are 3 columns, B, A, C, 3 columns. So let me call that as B. So yeah. Oh, there's a problem. What problems? Columns, I guess I have made a spelling mistake, I guess. Yeah, everything is fine. So if you display A is simply this. If you display B is simply that. Now, what will happen if you actually do A plus B? What will happen? So you are now seeing A as well as B. Let me make both of the at the same thing, at the same plot. So now we have this is data frame A, this is data frame B. What if you do A plus B? What will happen? Let's see. Well, it will try to concatenate whatever entries that are compatible. For example, A2 will be added with A12, and you will get probably 14. All the entries that have consistent indices, they will be added together. But all of them for which the entries were not available, they just get these nan values, not a number. So, but if you do this addition like so, you will come up with like so. So one way to do that is to say, okay, A plus B, that's whatever the result is, maybe that, dot fill NA with, let's say, 0. And the result is all the values that are filled with 0. Another way to do that is A dot add, call a function, A dot add B, and then give the fill value for NA if there is, let's say, 0 or something, or let's say minus 100 if you want, and that is also there. I mean, fill value is, oh, why these are minus 76 and minus 85 and minus, why don't I fill the value with some value like 0? A dot add B, and I get this. Yeah. So yes, so basically if I add A to B and I give this fill value 0, I actually get the result like so. I can give this fill value 0 here, or I can just do A plus B, and then whatever the result is a data frame. I can call this dot fill NA function on that data frame, and I'm happy to go with that. Further, we can concatenate multiple data frames together if you want. For example, we have data frame 1, data frame 2. If you want to concatenate them together, we can concatenate. The default concatenation is they are stacked one on top of the other, or if we want them to concatenate using column wise, for example, we want more columns to be added, we can just call the concatenate function and set the axis to be column. So yeah, I leave this practice for you. I mean, you can call this concatenate function, just generate the data frame 1, data frame 2, and you can call the concatenate function, and just you can just do the concatenation. Next important thing is group by. I really want to discuss this. Want to spend some time on that. Group by. How can we group different entries together? Let me first show you a scenario, and then I will actually explain the group by actually does what. So let me give you a scenario. Let me show you a scenario here in NumPy, here in Python. So let's say df is pd.dataframe. pd.dataframe. Let's say we have certain key is, let's say, list of ABC. Let's say these are our values for key, and then what we really have is so this. Then we have, let's say, the values val, and let's say the values are just the np.arrange. Let's say the values are 6 values, some I mean 0 to 6, these are the values, and that's our basically dictionary, or maybe the data frame with 2 columns. One column is key, the other column is values, and these are the entries in the first column, ABC, and the second column has entries 0, 1, 2, 3, 4, 5. We can set the column names explicitly. It's always good to do that, and that is basically key and well. Okay, so if we do that, we have our data frame df. So let's see what df is. So that is df. What if really you want the values of all A's to add up together, and values of all B's to add up together, and values of all C's to add up together. So for example, the value of A is 0 and then the value of A is 3. What if you want to add them together? You want to group all different keys together. So the group by essentially does the same thing. What it really does is the following. It will basically first split all the data and will pick all the rows of A. So in this case, A has two values. A has 0 value, then 1, 2, 3, 0, 1, 2, 3. Then A has 3 value. So it will first split with respect to all the keys like A, then all the B, their values, and all the C's and their values. So here we have just 2 C's and their values. Then, so if you want to group it by key, so df.group by key, which means group all the key values, all the records with respect to their keys individually. That's one group, that's another group, that's another group. Now if you call on each group, if you call a function sum, then it will add all these values together against the same group. So here against A, the value will be 4. Here against B, the value will be whatever the sum of these. And here against C, the value will be the sum of these, whatever that. So first you split to make groups, then you apply the function, and then all the splitted results, they combine again together to give another data frame. That's what the group by does. And you need not only to apply this sum function, you can have a mean function, you can have a standard deviation, you can have other statistics kind of functions, whatever you want to come up with. So let's run this command and see how it works in Jupyter. So let's see. So that's a df.group by. I want to group by my column key, and what I really want to do is I want to sum them up, and the result will be all these different groups. They sum, and remember this: they first get splitted, then the operation is applied, and then they merge again to a data frame, and that happens here. And in certain cases, it really becomes very, very powerful, this group by, because we may have to group a lot of things together. It may actually, it is sometimes used to actually arrange the data in a particular way, to summarize the data in a particular way, and stuff like so. So I mean, I can explain all these things in Pandas in much more, but I'm now going to basically reading a CSV file and going to apply whatever knowledge we have to actually prepare a CSV file for some machine learning or data science algorithm. So let's do that. And for that, I basically already have I have a data file for you. I have made that somewhere. Maybe let me see. Yeah, here. So I have actually downloaded this data file from basically machine learning repository, UCI repository. It is this particular file with a lot of fields. First column represent age, second column represent the job status. There's a third column for, there are actually 15 columns. We have descriptions of these columns as well in another file. So that's adult, this is adult data set that is basically available on in machine learning repository. So we have a lot of fields here: age, work class, FNWGT, education number, and a lot of fields there. And the data basically is a mix of both numerical values and text values and all that stuff. So what we are going to do is we are going to basically load this data to using pandas using pandas.read_CSV function. And then what we will do is we will be converting all these text values or text fields to basically numeric data somehow, and then we will be saving that file in the prepared file again in a CSV format. And we will be applying some tricks that we have learned using Pandas so far. So let's start. Let me just copy this path here. The path is this dull data. So let me copy that path and let me go back to Jupyter Notebook. So let's work with this file and see what happens. First of all, let me define a variable where I want to save this file. pd.read CSV function. That function is available. And here I basically read this file. Okay, I have placed this R in front of that so that I am forcing that these backslashes, they should not be confused with the escape sequences. They should be used, they should be considered as raw formats. If you now see, if you pick the, actually the data has been read. If you see the shape of the data, the shape of the data is, it has 32,560 records. Each record has 50 attributes or columns. If maybe you want to see the columns, what are the columns? What are the columns? The columns are, oh wow, the columns are 39, state go. What is that? Why are these columns? Basically what happens is this file does not have a header. So the very first record actually is acting as a column, although it is not, these are not columns. That is actually the very first record. I have to, when I call the function, read CSV, I have to force it that the header, there is no header. So don't confuse the very first, so I will place this header equals none. That means don't confuse the very first row as a header. Now you see the number of rows, they actually increased by 1 because the very first row, it was confusing that with column headings rather than actual data. Now this does not have any columns. So the default indices are basically starting from 0, 1, 2, 3 and all that. We can I mean define the columns. We can rename the columns. For example, columns equals to let's say C plus str x for x in range df.shape df.shape 1. So what this code does is it actually assigns column 0, column 1, column 2 as string names. So let's see. Now if we see df.columns, it basically becomes now the basically 15 columns starting from 0. Now we can access different, we have df, for example. We can access, let's say we want to see column 14, for example. What are the entries in column 14? These are the entries. If you want to know more and more columns, we can see those entries as well. So for example, column 14, then we want to see, let's say column 0, we want to see these entries. Oh, we cannot see that. Why not? Oh, basically we need to use a log function because we are accessing, if we want to access these columns, we should be using log function rather than these. So why don't we use log function? So .loc, we are going to use the explicit indices. Let's say C0, and then we want to use, let's say C14, and it again gives me a problem. Why is that? Maybe C0 key error, C0, that there is an error. I'm not able to actually see column 0 and column 14 together. Why not? That's a problem. I should be able to see those together. I can see this individually. Oh, I cannot see this individually either. Why not? Is there some problem? Let's say C0. that is there. So that is there. Why don't I if I, for example, use .loc and I call OK C14, what's the problem? Oh, these are columns. So I should first write the row index as colon because I'm accessing just the columns. So I should mention that access all the rows for this particular column. On the other hand, if I want to access, for example, 0, I will say, okay, access all the rows using log function, access all the rows for this particular column. Now, what if I want to see both these C0 as well as C14? What if I want to see? Maybe I can use the indices that I learned, an index array. I learned that in NumPy. Maybe I can use that and everything will become fine. Oh my God, yeah, it's working. See, now this is an index array, and that is, so I'm using the log function because these are explicit indices of columns and all that stuff. And so let's play with this data a little more. Let me just write, for example, df.head. That function actually is there that displays the top 5 rows of my data. So these are my top 5 rows indexed with all these kind of columns and stuff like so. Let me process this data more. For example, let me, oh, by the way, there is a tail function as well, df.tail, that actually give me the last 5 entries in the order. So let me see, for example, by the way, if I just go to the description file, the description file basically says that the task, if I really want to, if I tell you the task, here the task might be written somewhere. What do you really want to do? What predictions you want to do here? What's the task? So basically they have written the task here, what I really want to do with this data. So that's our data. And okay, so the task really is to find out the probability for the label, find out the probability whether a particular adult is earning more than 50K or not. So the values are more than 50K and less than or equal to 50K. So that's basically a classification data set. So let's see, and that's a 14th column in our data frame. Let's see that. So if we just see df, let's say C14 dot unique. If I just see what are the unique entries, these are the unique entries. If I just copy these unique entries in an array, let's say unique entries or labels, class labels as this. So if we now see the labels, label 0 is basically this, and label 1 is basically that. And these are the only 2 labels. So what if I really want to replace this label 0 with -1, and I want to replace this label, I mean, rather than these strings, I just want to replace them with -1 and 1. This is classification data. Why don't I use -1 and 1 labels rather than less than or equal to 50K as a string and greater than or equal to 50K as a string? So how can I go and change this particular column? How can I do that? First of all, let me find the index where this happens. So what is the index where this df C14 basically is equal to this particular value? What is the index? So that will be a Boolean index, yeah? That will be a Boolean array. Somewhere it will be true, somewhere it will be false. Now I really want to basically change the values where this index happens. So df C14 dot Boolean indexing in Pandas basically is considered to be, it resembles to explicit indexing. So you have to use lock function rather than ilock. Dot ilock index, and this particular index, you just place a -1. Okay, will that work? Yes, I guess. And what you do next is, that's a warning, don't worry about it. It is a warning because the slicing actually gives the same memory view in Pandas as well, and we are overriding a file using a sliced variant, so it is giving us warning that be careful about copy and view variants of Pandas. So next what we do is we take the complement of the index, so we just reverse true and false and place a 1 wherever the other class lies. So that's what we did. And now if we see df 14th column, column 14, it will give me the values -1, somewhere 1, somewhere -1, and all that stuff. So if we now see unique values, df in C14 dot unique, if we now see all the unique values are -1 and 1. And if we see now the structure of our data frame, it just have the last column, which was first showing as less than 50K, and now it is showing as -1, 1, -1, 1, and all that stuff. What next? What we do next is basically we are going to convert this a C1 column. It has a lot of, for example, different kind of job titles, state, government, self-employment. We're going to convert this C1 column using one-hot encoding. So one-hot encoding is basically sometimes used to convert the string data to numeric data for further use. So for example, and there's a function in Pandas called get dummies that actually helps doing that. So first let's see how many unique entries are there in that column. So df C1 dot unique dot size. So that will give me the total number of unique entries in that column. So this particular column has 9 unique entries. So when I will convert using one-hot encoding, this particular column will expand to 9 columns. So basically in place of one column, we'll be having 9 columns because there are 9 entries, and one-hot encoding actually, that binary encoding actually depends upon the total number of these types. So what I really do is df equals pd dot get dummies function that actually does that stuff for me, get dummies. And what columns I'm really interested in converting to one-hot encoding. Let's say C1, I just want to convert that, and that's okay. So now if I see df.shape, earlier my df.shape was having 15 columns, but now my df.shape has 23 columns because one column is gone and 9 more columns are being added. So 15 minus 1, 14, 14 plus 9, 23. Now if I see df.columns, if I see these are so many columns, C0, C2, and all these columns, but C1 column is now actually more than. So C1 this, C1 that, C1 that, and all these kind of columns. So that's what this C1 basically goes to. So 15 columns earlier, one column gone because C column is gone, and next C column is gone, and one column is gone, and 9 new columns are being added. So the result basically is 23. But here you might be seeing one terrible thing. What is this particular column? C1 underscore question mark. maybe there is a null entry in that column, and that null entry is also specified as maybe there are missing entries in there. Oh, I haven't encountered, we actually haven't encountered the missing entries. Let's go back and see whether there are missing entries or not. Right now we have changed this df, because we have copied this result to the df. We have overwritten that. Let's just go back and read the file again and see whether it has missing entries or not. If it has missing entries, we have to work about it maybe differently. So let's say that df. So let's say df df dot columns equals c plus str x for x in range, x in range, np dot x in range, let's say df shape 1. So these are my columns. So df c1 is null. Is that? Oh, it looks like false everywhere. So maybe we should call some function. How many null entries are there? Oh, there is no null entry. Then why that when I convert, oh, we were working on C2, I guess, or C1. Oh, C1. So why that? So let me see the unique values in that. df c1 dot unique. Let me see all the unique values. So, oh, one value basically is like this. So this is one value, this is another value, this is another value, and all that. And one value is just a question mark. That's amazing. Yeah, so it's okay. Whatever we were doing, we're perfectly fine. So df is, let me call that df2 equals pd dot get dummies. Df and columns. What columns we are interested in is basically, let me see, let me convert the C1 and let me convert the C14 columns as well. C14. In that case, both the columns, they will be converted from string to, so this column will be converted from string to one hot encoding, and this column will be converted from string to one hot encoding. And remember, this column just has two distinct entries, so 2 columns will be added because of this, and 9 columns will be added because of this, and the original columns will be deleted back. So, oh, what's the problem? Columns equals to, so that's what we miss. So if we now see df2 dot columns, if we now see df2 dot columns, it has several columns now. So several columns due to C1 and several columns due to C14. Let me see whether there are let me see whether there are null entries or not. So let me just yeah, I mean there are no, there are no there's no null entries. All the entries, I mean there are no missing entries. If there were missing entries, we could have taken care of those as well. It looks like there is no missing entry. Yeah, great. So one way to see the information of df is basically to just call the info function and see how many missing entries or other kind of stuff here. So column 1 has these many entries, all of them are non-null and stuff like. If there are null entries, for example, for a particular column, you might be seeing lesser number here than the total number. So now if we just see df2 that we did the one hot encoding for, df2, So that df2 looks like that. It is pretty much like same as earlier, but if we see some of the columns like the columns here, all these columns, they previously were strings, but now they are converted to binary numbers. And we can apply further processing on these binary numbers, or maybe using scaling and pre-processing that we do on data, and to do it more. We can convert a lot of columns to their one-hot encoding just at once. We can if we don't want to convert the one-hot encoding, just we want to loop over unique values, we can assign them numeric codes by ourselves to convert the data to numeric form. And the reason is the machine learning algorithms, they really require the data in numeric form. So we can convert, for example, all the columns. If we want to write all the columns that contain strings, we can convert all of them just with one command to one hot encoding if we want, by this function getDummies. There are several other functions as well. So let me write this data frame into a CSV file. Let's say df2 dot let me do cs to CSV. Let me write that to CSV, and let me write the name of CSV as where should I write that? Let me write that in, again, a data folder, in this particular folder. Let me copy that, Control C. Let me write that file here. So R, Control V, and let me write that file name as abc.csv. So this file should have been created there. A little modification that we have done, you should see these modifications in this particular file. We can open up this file in Excel. Yeah, if you really want to see that, let me just go and format to fit column width, and so that's the original file. These are the columns that we did not disturb, and these are all the columns that we actually converted to one hot encoding, including the class labels there. You can further read this file at some other time to make it more, to process it more and stuff like so. So I'm pretty much done here. I can discuss more on that. Basically, we have a full-fledged course on Pandas, as well as the visualizations and plotting and graphics and all that stuff. We have full-fledged course on that on AI Sciences. So, but in this short video, I just covered a few of things, not all. But if you are really more interested, you should enroll that course and get details, bit by bit details of all the functions and many more functions that we haven't discussed here due to the shortage of time. So this wraps up this video. Basically, thanks for watching. If you really like this content, please press the like button, subscribe our channel, press the notification button so that you are being notified for our upcoming videos as well. So share among your friends and other people to promote this content, and yeah, good luck.